here's the problem as written in the textbook. So it wants us to consider the problem of determining whether a given undirected graph G with vertices V and edges E contains a triangle of cycle length 3. And there are two parts to this. So it wants a O of V cubed, as in the number of vertices cubed, algorithm to find a triangle if one exists. And then it wants us to, after that, improve the algorithm to run an O of V times E, vertices times edges time. And we can assume that the number of vertices is much less than the number of edges. Okay, so, all right, so let's try to understand this problem for starters. So remember, it's undirected. So we'll just write the data that we're given is a graph. It's undirected. And we have a series of edges and vertices. So it's just a graph. Right? And then the unknown is there a triangle? In the graph. And then the last thing is the conditions. So the triangle has to be length 3, which is the definition of a triangle. So I'm not going to write that out. We're doing part A first, so we want our algorithm to run in O of V cubed time. So and we want our algorithm in O of V cubed. Okay, is there anything I'm missing here? No, I don't think so. All right, so let's draw a couple examples and see if we can understand better what's going on here. Okay, so I'm just going to draw a graph. We know we're in the graph theory section. The question is explicitly asking for a graph, and it's asking for does it have a triangle or not. Okay, so let's just draw something really simple, like we'll draw a square and then a triangle and see what happens. Okay, so does this have a triangle? Or does it have a cycle of length 3? No, it doesn't. And the reason is because even though it does have a cycle, it has a Hamiltonian path, it has a cycle, it has whatever you want to call it, but it doesn't have a triangle. And the reason is because from any vertex, if you just take 2 steps or follow 2 edges to the next one, you have not encountered the same vertex again. So it's not length 3. But we do have a cycle of length 4. We have several, well, yeah, one cycle, depends on how you define it. All right, so that's that. That helps us understand it a little bit. Now let's look at a triangle, like literally just the shape triangle. All right, does this have a cycle? Or rather, does it have a triangle? Well, yeah, because from any vertex, if you just follow 2 edges or 3 edges back, then you get back to that same vertex. So this has a triangle. Okay, so I think we can just add some stuff here to play around with it. These don't really matter. We're just kind of adding stuff. So the really defining feature is this part here. This is what we're looking for, regardless of how it's viewed and what's around it. All right, now, just using, okay, so what are the various ways we can solve this? So just thinking about this from the perspective of what we have available. So we can explore it using like DFS or BFS. We could like topologically sort it. We could look for components. We can do many things like this. But the tools that are most at our disposal are these exploratory ones that require looking at edges. So like the usual approach we take for any of these problems is looking through the tools at our disposal to see if we can come up with an analogous problem. So a way to simplify this down to a problem that is similar to what we're looking for. So tools are algorithms. So we have DFS, which is good for cycles. Ooh, that's interesting. We have, what else is it good for? Oh yeah, component analysis. So seeing if there's any multiple components or where the articulation vertices are, if there are some. We have BFS, which is good for finding distances. We have topological sort. Which is really a specialization of DFS. And that's pretty much it. So let's look at these and see what they will do. So DFS will find a cycle. This, kind of jumping ahead of it, this will be, let's just kind of put that to the side for now because that'll be more useful for part B. And then component analysis. Well, component analysis is not really useful here because if we have our triangle, then like the triangle has to all be one component. And even if we have two triangles in different components, that doesn't matter. Like if you had a graph like this is all one graph. The fact that these are separated into two components, it doesn't tell us anything. So we can kind of safely say, for now, that DFS, at least with an adjacency matrix, is not too useful. BFS. Well, distances, that might actually be useful. But the problem is BFS is also O of V plus E. So we're going to kind of punt that for part B as well. So let's just say for now, BFS doesn't really help us. And then finally, topological sort. Well, we're not looking for a sort at all. We're just looking for triangles. And there's no part of topological sort that specifically helps us that DFS doesn't already have. So, okay, crap. Now what? So we've scratched out everything we've written, right? Well, okay, so our usual tools aren't working. So we have to step back a little bit and think, how can we think a little bit more outside the box? The solution might have already come to just by looking at the constraint, but the constraint in this case might be helpful as well. So the constraint here being the O of V cubed runtime. So whenever we see a exponent on an input source, what do we think of? Well, there could be, generally what it means is that for every input or every datum, we're looking at every other datum. So if we're given a set of like A, B, C, D, then for A, we have to look at B, C, D. For B, we have to look at A, C, D, or just C, D. For C, we have to look at A, B, D, or just D. And then for D, we look at all the others, or just D itself. And both of those, the ways I just described that, in both cases, it's going to be an O of n squared algorithm. So what would O of v cubed here mean? Well, it means that for every vertex, we're looking at not only every other vertex, but also every other vertex. So for every pair of vertices, we're also considering every other vertex. So that's just like a very kind of high-level way of modeling that. Now, how is that useful to us? Well, if we have an adjacency list, it's really not, because in the adjacency list model, where you have your vertices, let's just model this as A, B. I'm going to erase this. It's not very useful anymore. So when you have your adjacency list, like A, B, C, D, and then you have, let's say we have A pointing to all the other B, C, D. Let's say B points to C, C doesn't point to anything, D points back to A. So what this would look like is like A, B, C, D, and then A points to, oh, this is undirected, I'm sorry. So, yeah, so this would also have A. C would also have A and B, and D would also have A, right? Okay. So A points to B, points to D, points to C. B points to just C. D points to A. Okay, so that's our completed graph right there. So in this model, if we want to compare every vertex, every pair of vertices to every other vertex, we have to walk through not only every vertex, but also every edge. So to see if there's an edge there. So this would actually be an O of V, like if we wanted to just walk through every pair of these vertices, it'd be O of V cubed times E, which is no good, and that's even higher than our already ridiculously high runtime. Like O of V cubed is basically all bets are off. It's still polynomial, but it's not really that good. So that's no good. But remember from the textbook, one of the things that was described is that we have multiple ways of representing edges and the connections between graphs. So, and just thinking of this from the perspective of bottleneck analysis, we had this slightly too slow way of running this, where we look at every pair of vertices and compare that to every other vertex, or consider it alongside every other vertex, but we had to walk through every edge for that vertex to be able to consider it. And that gave us an O of V cubed times E runtime. Or it's something like that. I don't know exactly, but suffice it to say it's too large. I'll just write that. So now we want to reduce the bottleneck here. And the bottleneck here is the edge, right? Like we want to get rid of this term. This part's fine because we already have that in the book. So how can we do that? Well, if we're working with the representation of the data and we're looking for a way to speed it up, it's this kind of analogous to working with a hash table or something like that. Like a hash table is a way of speeding up the access of something. So what's our way of speeding up our access into edges between vertices when we have a graph? Well, we don't have hash tables. We could, but it's not really the point here, and it wouldn't really help us anyway. But what we do have is adjacency matrices. Adjacency matrices give us very fast lookup of is there an edge or not. So remember, the book describes adjacency lists. which are good for exploration problems, and basically everything else. Like they're sort of the catch-all. And then there's also adjacency matrices. And these are good for just quickly checking, is there an edge between two vertices? Oh, so if we're looking to reduce the bottleneck of checking, is there an edge between two vertices, then the representation that is specifically designed to quickly check, is there an edge between two vertices, seems ideal. And this happens in O1 time, because, which I'll explain in a moment. Whereas in an adjacency list, if we want to check if there's an edge between two vertices, it takes O of E at worst. That's assuming that the access into the adjacency list for the vertex is O of 1. And then we just have to scan through all the edges to see, is there an edge from this vertex to that other one. Or in the worst case, you might have to look from the other vertex. So if you have like vertices U and V, and you want to see, is there an edge between those two vertices by adjacency list format, then you may have to check in a directed graph at least, in the adjacency list of U, is there an edge pointing to V? Or in the adjacency list of V, is there an edge pointing to U? But because we're undirected here, that's not really important, so we're not going to consider that. So suffice it to say, in an adjacency matrix, the access time is O of 1 for just seeing, is there an edge between two vertices, whereas in an adjacency list, it's O of E. And our bottleneck, remember, was, will we be able to see this? I'll write it over here. O of V cubed E. That was our bottleneck, and it was because we were doing this. And it was because we were doing this, using the adjacency list with its O of E runtime. Okay, so what this tells us is if we switch our representation to an adjacency matrix, then we should be able to appropriately like knock down our O of V cubed E to just O of V. Okay, so let's see what happens when we do that. All right, so let's go back to our drawing before of our vertices and our adjacency list. So let's say A connects to B, connects to C. So this has a link to A, C has a link to A, and then D has a link to nothing. Okay, so we want to convert this to an adjacency list. So I'm just going to run through this real quick just so you can see, like you can completely understand why this is better in some cases. So A, this is too small. Can you see that? Let's draw it a bit bigger. A, B, C, D. A, B, C, D. All right, so it's going to be identity for sure. It doesn't really matter how you actually represent this. The fact that, in fact, you might want to just say 0 because edges or vertices are not connected to themselves. So this will be 0, 0, 0, 0. Okay, and then we knew that A was connected to B. Another thing you can do is just split it here, and we'll never consider that. It's really just a matter of how you represent the data. It doesn't affect the actual complexity at all of the algorithm. And then A was connected to C. B was not connected to C, and D was not connected to anything. Okay, so what this enables us to do is now if we want to see is A connected to B, then we can just check, okay. So the position of A, like if we know that A maps to 0, and B maps to 1, and C maps to 2, and D maps to 3, then if we want to know does A connect to B, and I think that's the way you represent undirected edges. So is A connected to B? Then we can say, okay, is our matrix at 0, because A is mapped to 0, A maps to 0, comma, B, which is mapped to 1, is this 1 or 0? Or is it at least higher than 0? So we see, okay, 0, so the row 0, which is this one, and then the column 1, which is this. So yes, it is. Okay, so now with this representation, we can just consider every pair. So just pseudocode for this. This should be really simple at this point. We're just considering every pair and then every other vertex not already in that pair. So for I in vertices, for J in V not equal to I, for K in V not equal to I or J. And then we just want to know if, return if, the matrix between, and by the way, we want to know if there's no edge between these, then we just continue. So I'll just draw that out too. If there's no edge, E, which is a member of E, where E equals I, J, then continue. Okay, and then for K in V, which is not equal to, oh, that's not an edge, that should be just a list. And then return true if there's an edge from K to I, and there's an edge from K to J. Whoops, that doesn't look like an E. Okay, so that basically handles this basically solves our first question or A. So what we're doing here is we're looking through every vertex for I and V, and then every vertex that is not I, looping through it. And then if there's no edge connecting those two, then there can't possibly be a triangle that involves those two vertices. So let's just continue from that point. And then if there is an edge connecting those two, then we loop through all the other vertices that are not I or J. And if there's a vertex, or if there's an edge also connecting that third vertex to both of those other two vertices, then that means we've got a triangle. Now let's do the runtime analysis. So this will be O of, let's use green for this to make it more clear. So O of V, and then this will be O of V. Now just to be abundantly clear here, just taking out one vertex would still make it complexity V overall. So it's not going to be like V minus 1 or anything like that. This operation here of checking if there's an edge because of our adjacency matrix is now O of 1. But this would be, this is the slow part otherwise, so with an adjacency list, would be O of E. As would this too. So we might actually have like O of V cubed E squared or something, now that I think about it. Let's just complete this analysis and then figure it out. Continue is obviously O1, and then this operation here is O of V. And then this is also O of 1, just checking if there are two edges. And the fact that it's done twice doesn't matter because that doesn't become larger with the number of inputs. So our total runtime here is O of V times O of V, O of V times O of V times O of 1 times O of V times O of 1. So that works out to that's O of V times O of V times O of 1 times O of V times O of 1, which is equal to, you guessed it, O of V cubed. Okay, so there's our algorithm. Loop through every pair, or rather convert to, one other thing I didn't cover here is the conversion to an adjacency matrix. So that's a little bit of a contentious issue here. So the one assumption we're making here in that conversion, here is that the conversion to the adjacency list is an O of V plus E operation. So but the thing is, if that was true, then if that was true, well, this conversion here is O of V plus E. Hopefully you can see why. It's because we have to loop through every vertex and every edge and then write that edge or add one to the matrix for that. So whereas the converse is O of V squared. So anyways, the total complexity given this would actually be O of V cubed plus E, right? Because we still have to convert to E first, or we still have to convert to the adjacency matrix, and then do our algorithm that we just described in the pseudocode there. And the reason we're going to ignore this, just to comply with the question requirements, is because we're going to assume that that V cubed is always going to be significantly greater than E, which is always true because the most number of edges we can have is V squared if the graph is complete. Now let's take a look at part B. So what tools do we have at our disposal when we're dealing with these kinds of situations and problems? So we have our DFS, we have our BFS. Remember, DFS is good for cycles and components, and BFS is good for distances. All right, so let's walk through how we'd solve it with each of these. And this isn't necessarily exhaustive either. So, and by the way, remember our problem in this case, just to refresh you, was to improve the algorithm to run in O of V times E time. And we can assume that V is significantly less than E. So in the case of DFS, it's good for finding cycles, which is the exact problem we're looking for. So how would that look? Well, we'll come back to BFS. So let's draw out the simplest example just to illustrate how this would look. We'd have our triangle. The graph is literally just a triangle. 1, 2, 3. And DFS would start us off in any vertex. Let's just start from here. And then it would explore out, and then that would keep exploring in this case. So, but then we couldn't keep going because that would be a back edge. So along the way, we'd be recording parents. So this would point back there. This would point back here. And then from here, when we encounter this back edge here, we could then follow our parent pointers back up to this starting vertex. So that's the basic gist of it. And that seems like it could work. So we'll come back to this. Now let's see what would happen with, oh, and just by the way, if the back edge is parent's parent is not the vertex that you encountered, then it's not a cycle. So that would happen in a case like this, where you have an additional vertex here, and that would point back here like this. So when you encounter this back edge, you would follow the parent to here, and then the parent to here, but that would only take you here. It wouldn't take you to there. And since these two are different, then we know that there's no triangle. Remember, this still looks like a triangle, but it is not the definition of like a graph triangle because it's not a cycle of length 3. And that's because I added this vertex here. All right, now let's consider BFS. So you might think that BFS would be able to handle this just as well as DFS. And, you know, it kind of intuitively makes sense. We keep parent pointers when we're exploring with a BFS, and we keep times and distances too when we're exploring with BFS. So let's play around with this. So let's draw our triangle again. Same one as before. And we'll start from here when we're exploring. We'll go out to here, and this will set a parent pointer back here. Then we'll explore out here, and this will set a parent pointer back out here. And then because BFS will explore in a breadth first way, given the name, we're going to hit this edge here last, this edge. So, because we went to this vertex first, we're going to be exploring from this direction like that. So we'll go from this vertex to this vertex, and then we'll see we've already encountered a vertex. So, okay, well, this one's parent is the same as that one's parent. So, okay, maybe breadth first search will work. Okay, interesting. How else can we do this? Well, we could try recording time too, which is something that's very common in BFS. So we'll record this as 0, and then every time we explore out, we just add 1 from wherever we came from. So we went here first, we record 1 there, record 1 time here, and then when we're exploring this edge, we'll add 1 to that time without actually explicitly recording it onto a vertex. So we'll be kind of in this like 2 quasi state from here to here. Now, so this looks like there might be something there too, because in this case, the 2 minus 1, because the times are like, will tell us at what time we hit something. So the 2 minus 1, maybe that pattern, if it's equal to 1, or that equation when it's equal to 1, means that there's also a triangle. So let's write that out. So time explore minus time of target or next equals 1. And then we can say there is a cycle or a triangle. Okay. So can you see the logic there? We went from 0 to 1 for each of these for a breadth first search, and then as we were exploring this edge here, we were kind of in this quasi-2 state. And then we said, okay, the number that we're in the quasi state of minus the vertex that we're encountering, if that's equal to 1, the difference between them, then that means that there's a triangle. Now let's explore what happens if we add more vertices here. So we'll add this here and see what happens. So our times are no longer correct. Let's fix that for starters. So this would be 1 now, and this would be 2. And then this will have a parent pointer back to the starting vertex. All right, so now, so we're going to explore, so we explored this way to start with, to each of these 2 1s, because we started here. And then the next thing we're going to do is, because we went here first, we're going to explore this way. And that'll record the 2 here. Oh, this parent pointer should actually point back here now because of the direction or the order we went in. And then from here, this one down here, this vertex down here, we're going to explore this way too, and we'll encounter a back edge. Okay. Now what? So during this exploration, we were in the quasi state of 1 plus 1, because we came from 1, but we're adding 1 because of the additional exploration. And we're encountering a vertex of time 2. So 2, using this formula, the time that we're exploring from is 2. And the time that we're encountering of the vertex is 2. So this will be 2 plus 2, or 2 minus 2, which is 0, which is not 1, so there is no triangle. Okay, so that seems to work so far too. Now let's see what happens when we play around with this in a more advanced graph. So if you're playing around with this on your own and you're like trying to understand what's going on here, you're going to have to play with a lot more graphs than what I'm putting up here. We're just going to go straight to, we're just going to pretend that we designed a bunch of graphs, and this is kind of the most interesting one that we came up with, and we'll examine how it behaves under DFS and BFS. So we'll start with DFS. Actually, let's start with BFS because it's top on our minds right now. Okay, so again, we played around a bunch. we found some graphs to just confirm or see what happens with our hypothesis here. And the one that's most interesting that we came up with was this. So let me just see if I remember this correctly. Oh, this is not. This should be down here. This should be down here. Okay, and these are connected, and that should do it. Okay, now let's see what happens if we BFS, and we'll just take, for example, A. You could run this BFS on multiple different places, and you will come up with different answers depending on what happens. But I'm just going to jump straight to the one that is significant and brings useful information to us for the purpose of this question. And by the way, if you're thinking about ways to just play around with these graphs, you can think of things like, just it's kind of like testing if you're a software engineer. Like you just think of every potential edge case you can think of. So you might try a vertex. You might try a vertex connected to another vertex with one edge. You might try a star like that or something. Well, it's a pentagram, but whatever, you know what I mean. I don't know, is that complete? Yeah, this is a complete graph too. You could try a bigger complete graph. You could try a complete graph connected to another complete graph. Like this is the way you figure out these kinds of questions, is you just try all these really wonky things to make sure that it works in every case. You don't want to go too far with it because at some point you're just kind of wasting your time and you want to just check the solution or something instead. But just playing around with these kinds of things, or maybe a square. I already did that before. Like when I had that triangle thing I just showed you a minute ago, and I added that vertex on the bottom just to see what happens if I broke the cycle. That's actually just a square. I just didn't draw it as a square. It looked like a triangle. But you could redraw that same graph to look like this. You could draw a path. So that doesn't have a cycle, but you could just add a cycle somewhere and see what happens, or you could add a triangle down here and see what happens, et cetera, et cetera. So we played around, and we ended up with this graph here, erasing all this, because that gets the point across. So we arrive at this graph here. Now let's BFS from A. So, okay, so first thing that happens is we explore out to B. So whenever I'm breaking a tie, in this case we have a tie between B, C, and D, for the next one after A. In this case, the way I'm going to break the ties is just by picking the one that's closer to A in the alphabet, or like lower in the ordinal order of letters. So we'll hit B, and that'll give us a pointer back here. We'll record times along the way too. So this will be time 0. This will be time 1. Okay, and then we'll hit vertex C, and that'll take us back to A with time 1, and then we'll go to D, which will again write a pointer back to A with time 1. Okay, great. Next is B. So every time we hit one of these vertices, remember in BFS, we're going to be queuing up all the next edges and vertices for processing after these have all been handled, because the underlying data structure is a queue. I'm not going to draw that out. I think if you're doing this question, you should probably understand BFS enough to be able to figure that part out. But if you can't figure that out, just leave a comment and I'll link you to a video, or you can check it on YouTube or something. Anyways, so then from B, we're going to go to F, and that'll again write a pointer back to B with time 2 this time. And then that'll also that'll queue up G. And then D, from D we'll go to H. So that'll write a pointer back to D with time 2. And then from F, because G was the next queued up, or the edge from F to G was the next queued up one, we'll write a parent pointer back there with time 3. Okay, And then from F, we're going to see that we've already encountered H. So this is kind of the magical edge right here. This is where we what we can call the back edge. Okay, so what happens here? Well, the algorithm that we came up with was time 3 minus 2 equals 1. So the time here is 2, the time here is 2. And so the time here is, the difference in time using the formula that we wrote up here is 1. So that means that we do have a cycle according to this, which is good. Now let's see what happens if we explore this from a different direction. So instead of from A, from somewhere else. We'll see if the position affects it at all. Okay, so let's start the exploration from G instead, or C even. It doesn't really matter, they're effectively the same thing. So we'll start from G, and we'll go to F so we'll have a timestamp of 0 from G and 1 from F, and then 1 from H. Parent pointer is back to G. Ooh, and there was an edge here, because without this there wouldn't be a triangle at all. Okay, and then to C. Oh, so I'm actually breaking the order that I was doing these in. So we'll just keep going with arbitrary orders the way I was just explaining it, and forget about the using the alphabetic order as a way to break ties. So it'll just be random from now on for the purposes of this. Okay, so F to B. That'll take us this way to, I'm not going to explain this, I think you can figure it out. Okay. Oh, and when we hit C, so actually, you know what, let's erase all this because I forgot the edge. When we hit C, this is not here either. Okay, so we hit all this, and then F, when we hit F, we queued up both of these edges. Now let's assume we hit this one first. Okay, so our time here is 1 plus, so our for our equation, our time 1 is 1 plus 1. The 1 is from the time registered on F, and the other one is just, we add 1 every time we're exploring. And the time 0 is at like the vertex that we're hitting. Let's not call that 0, let's call that, so we'll call these T prime and TV. T prime is the time that we're exploring at, and TV is the time of the vertex that we are arriving at, and that's 1. So T prime minus TV equals 1. So there is a cycle. Okay. Yeah, that seems to work. Well, what happens if we come from D instead? Okay, so from D, we're going to explore, let's sort by, or let's pick break ties by alphabet again this time, just to keep it simpler. So 0, 1, 1. Then we'll explore here. So B and C are both at 2. Okay, and then G and F are both at 2. B encounters a back edge of F, but there's obviously no cycle here, so we check like the times or something. And actually, this is the one that's important here. So the reason this doesn't work is, as you can see here, as I was saying, there's obviously no cycle here, but what happens is the time here, the quasi-time at this like quote-unquote back edge, is 3. So 3 minus 2 is 2, or 1, and that means that according to us, there's a cycle. Okay, so that doesn't work. That's what we're really looking for here. So if you explore enough of these counterexamples, eventually you find something like this. So now we can say, okay, BFS does not work for this problem. Now let's try DFS. And we're going to reuse this same graph too. All right, so let's DFS this graph now. Let's start from A. So A will go A, B, F, H, D, and then it'll encounter a back edge. So we'll just write the parents along the way. Let's not record times for now. I don't think it's necessary. And this is a back edge. Okay, but the parent, remember our algorithm for DFS was the parent of the parent whenever we encounter a back edge. So the vertex that we're coming from, we check its parent, and then that vertex's parent. And that should be, if there is a triangle or a cycle of length 3, then that grandparent of the cycle of the vertex we're coming from should be the vertex that we are arriving at, that we are encountering via the back edge. Okay, and then we follow these pointers back from D to H to F. And F is definitely not A, so good so far. That is what we expect. So let's keep following this. So then we go to H, and then H has an edge to G. So let's set this parent that way. And then G has an edge to C, so we'll set C that way. And we encounter another back edge from C to A. Okay, and then we say, okay, what's the parent of C? G. The parent of G is H. So, okay, also exactly what we expect. There is no cycle there. And now we follow this. So then we go to G, and then it has the edge this way to F. And we encounter another back edge because we're already processing F. Okay, and now we say, what's the parent of G? H. The parent of H is F. F, which is the grandparent of G, is also the back edge, the vertex on the other end of the back edge we just encountered. So that will tell us there's a cycle. So, okay, cycle. So we started at A. Good so far. All right, let's try a couple of other starting points, just to be sure. So in the other example, D is where the thing fell apart. And I don't think it's fair to compare them equally because in in that case, it was a distance-based thing that just happened to work out over here. But in this case, for DFS, we're looking at parent pointers. But we'll still try it anyway. It's just we're not expecting that when we get to over here, it's gonna look the same at all, and it's gonna thus break the algorithm and say we can't use it. Okay, so we'll start from either do G or D. Let's do D first. Okay, so we explore to A, B. Actually, we end up in the same situation if we explore that way. So let's start from G instead. So we go G to H to D to A to B to F to H, G, H, D, A, D, B, F, H. Yeah, so I'm just trying to wrap my head around this again. So we go G to H to D, oops, wrong way, to A, to, let's go this way actually, C to G. Well, we've already encountered G shouldn't really have a parent, so we're just going to erase that. So I'll just write a 0 here. Okay, and this will be a back edge, but then we follow the parent and it's not, so that's not a cycle. Great. Let's just color it again. Okay, and then, right, so from A we followed C, let's follow B instead. So B's parent will be that way, F's parent will be that way, and then we could either encounter H or G. If we encounter G, then we follow the parent, and that's nothing, so that's useless. That's not a cycle, rather. I mean useless because we want to find a cycle here, but it's telling us there's not. But that's okay, there's still another edge we can follow. So let's draw that being this again. Okay, so but remember, we followed the pointer to the pointer, which is A. That's not G, so that's not a cycle. So we go to this edge instead. That's also a back edge. Okay, so now we follow, well, this is no good. So we follow H's parent, or rather we follow the parent of F to B to A, and A is not G, A is not H. So, well, we just broke DFS. Yeah, if we do DFS the wrong way, we can't do that either. Well, what the hell? What do we do now? Well, it turns out this entire approach was basically the wrong way. So what do we do now? Well, let's look back at the question. So if you're ever in doubt and you don't know what to do next, look back at the question, because oftentimes if you're not using something that is in the question, then you're going about it the wrong way. So the first thing you can probably notice is look at the runtime in the question. Now the question again is improve your algorithm to run in O of V times E time. We just checked out DFS and BFS, and for both of those algorithms, the runtime is, if you remember, O of V plus E. So that's better than what they're asking for. And they also mentioned that you should assume that V is less than E, and that should have no bearing on the runtime of DFS or BFS. So we can see from that we basically took this whole detour that was like kind of wrong. Oh, and then the last detail, take a look and see if you can see it. There's at least one more that I see. So remember, the question again is improve your algorithm. Improve your algorithm. So they want us to improve the one from part A. That might mean rewriting it, but in this case it doesn't really, because like you want to reuse the algorithm from the previous question if you can, instead of completely starting over for the next one, because that's hinted at in the question. Okay, so let's go back to the original. And just to be clear here, it broke when we started at G, or whoops, from A. From G, it broke. No. All right. So back to part A. What we basically came up with in part A was a loop of, it was for each, let's title this, so part A. So each pair, which is O of V squared, because any loop where you're accounting for two elements together, so comparing every element to each other, is going to be O of n squared. So in this case, our vertices are n, so it's O of V squared. So for each pair, at worst, that we then check each other vertex, O of V. So that gives us a total runtime of O of V cubed. That was our part A. Now, how can we improve this now? Instead of just starting over from DFS and BFS, which might have been your first intuition and was actually mine too when I first did this, how can we improve this to be better? So let's run through this. So each pair. Well, what do we know about each pair of vertices? Each pair that we want to check. Well, in the previous write-up that we had in the pseudocode, just breaking this up a bit more, we didn't just have each pair. Like, we weren't just comparing directly each pair. We were then checking, is there an edge? And then if there was not, we would just break or continue to the next pair. So is there a way we could speed that up? Well, if we know every edge beforehand, before going through every vertex, the vertex pair, then we could use that. So, okay, how can we generate that? Well, going from extracting every edge from every vertex in the adjacency list. Let's say we just have let's say we just put them in a list, like a linked list or a vector or something. So we would have our edges, and it's just a list. And then for each vertex, we want to put its edges into the edges list here. Edges. So all we're doing here is we're walking through every vertex and every edge of every vertex. Just make this more clear for each vertex edge. Push the edge into this list here. Okay, and great. Now, what's the runtime of this? So O of V, O of E, and O of 1. Okay, so the runtime of just extracting every vertex and edge is O of V, E in total, which is great. That's what we were looking for before. So that's a hint. It's not necessarily a tell, because this could still lead you astray. But the fact that we got a runtime that is the same as what we're looking for in the question is a hint that we're probably on the right path here. Okay, so we have our algorithm for extracting the edges. Now we can go back to so part B improve A. Okay, so we get our edges from the vertices. So we'll just say this is a function that takes our vertices and then gives us back a list of the edges. This runs in O of V times E, as we just established. And then the next step is to walk through each edge. Oh, what now? Well, in part A, all we did was check if for every vertex that is not, so what we did in part A was, the last step was to check every other vertex not included in that pair to see if it had an edge connecting to each end of those two vertices. So we have like a pair here and here, and we're comparing to every other vertex. So if this is our pair that we're working with, like our current pair, this is our like I and J, and then maybe this is our K, which is the innermost loop. We would check, okay, does this have an edge connecting it to either I or J? No, it doesn't, so continue. So that would take us here, and let's say there's actually an edge here and one here. So we'd go here to J, this is our new J, and we'd say, okay, there's no edges connecting it, so move on again. Here's our new K. Oh, and it does have an edge connecting each of them. There's an edge from K to J, and there's an edge from K to I. Now, if we know the edge, then we know what's on either side of it. So all we have to do now is we check is the edges U so this should be for each other vertex. So we want to see is vertex from this vertex, this is our K, to the edges U. That's the one end of the edge, a member of edges, and is vertex edge V a member of edges? And if so, return true. And then if this all fails, we just return false, which I should have written in the part A, I'm sorry. So just to reiterate, we're getting all of our edges. We do that in O of V times E. Then we iterate through all these edges that we just got. And then for every vertex, we should say is not in the edge. So we want to make sure the vertex is not either side of the edge, because then if there was an edge connecting it to something else in that edge, then that doesn't tell us anything, because that just tells us, remember in this case of like these two being I and j, if we're just making k equal to I, then yes, they're both connected, so it doesn't tell us anything. And something can never be connected to itself either, at least in this case. So that wouldn't help us anyway. We could just continue, or we could not handle it. It doesn't really matter. All right, so then the next step is to go through every vertex that is not already part of that edge. And then we check for that vertex, is there an edge connecting to the one side of the edge that we're considering, and another edge connecting to the other side of the vertex we're considering. So in this case, just draw a few more vertices to make it clear. Okay. So, ooh, this should be a J. Let's draw that better too. All right, so in this graph here that I've just drawn, in this algorithm, edges will be every edge here. This one, this one, this one, this one, this one, this one. For each edge, we're iterating over every edge. So in this case, the red one here is our edge that we're considering. So this is just like a snapshot of state is what the color is intended to represent. And then for each vertex, so we're considering this vertex and then that vertex and then that one and then that one. And then for this snapshot of state, we're considering this vertex k. And then we're checking, is there an edge between the vertex k and the first part of the edge? That's this. So that would be this green line here. And is there another edge connecting that vertex to the other end of that edge that we're considering, which would be j, so between k and j. And then if that's true, then we just return true because we know that there's a cycle. And otherwise, if we never encounter this situation, then we just return false because there's no cycle. Now, what will happen, let's just confirm this actually works. So we already kind of did in part A, and this is just an optimization, so it should still work, but let's just run a couple of examples anyway, just to make sure. So let's say this is our k instead. We are considering this as k. So vertex is k. Is there an edge between k and the edge u? No. So we just keep going. Let's say this is like our last vertex, so this is our next one. You know what, let's make it, yeah, that's good. So from here, this is our new vertex k. So for each, so is there an edge between the vertex and the first point, or the first vertex and the, is there an edge between the vertex and the first part of the edge? No, there is not, but we'll just go to the next one anyway, the next part of the condition anyway. There is an edge between the vertex and the other side of the edge that we're considering, the red one here. But because this is an AND condition, we're not going to return true because this is not going to work. So we'll just keep going. And I think we can see that down here won't work, or rather it won't return true. So we just end up here, and we just end up in the situation we had before where we detect the two edges, and that'll be handled correctly, and we return true. All right, so let's just examine the runtime now and see if we missed anything. All right, so for each edge, that's an O of E operation. For each vertex, that's O of V. Just these checks are static. Oh, so if we're, right, so we're going to have to do the conversion again to matrix adjacency matrices to make these constant time. So we'll just write this as constant time. I'm not going to explain again how to do that. Suffice it to say that it'll work out because we already explained that in part A. Returning true is O of 1, returning false is O of 1. Okay, so let's tabulate this. So our O of V times E plus O of V times E times O1. So that's just like 2 O V times E, which is just O of V dot E, because in big O we don't consider the constants except for O of 1. And there's our total runtime. Okay, so we're pretty sure this is correct because we tried it. We could go more crazy on the reviews and just make sure that it works on other examples, but I think that's sufficient for now. We looked at all the data, so you may assume V is less than E. Yeah, okay, so yeah, so we kind of used that. The bounds, right, so we used the bound between the conversion between adjacency matrix and adjacency list. So we've used that data. We've got the exact runtime performance that they're looking for in the textbook, so I think we've solved it. And there's our solution. Great. I hope you guys enjoyed that. Let me know if you have any questions in the comments, and hope that helped you.